Object state is a set of its data attributes and a set of the corresponding values that these attributes currently contain. So here in this little example we had a variable named today, which type corresponds to this data structure named date. So this is an object and this is the structure that describes it. Likewise, integer is a primitive data type, so it does not require a formal description. It's already built into the programming language and can be understood directly by the CPU of the computer, but it has a name, and that's also a name of an object. So the value of this integer obviously is pretty primitive information about its state. Likewise, the today variable would contain certain information about the month, day, and year, and with changes that may take place here, its state will be changing as well. And we can envision perhaps this demonstration that the variable name that represents this object essentially provides a connection to an object which is located somewhere in memory. I will try to draw it like a 3D box in memory, and this box basically contains the data attributes that correspond to the overall object state. So if we attempt to change these properties, clearly the state of the object will change. One example of a dynamic property is that one of these attributes could be actually a pointer to another object, right? So objects could have references to each other or pointers to each other, and so I may have another object right here, perhaps, which is dynamically allocated at runtime, and it reserves memory for some kind of text, right? So I can store characters here, A, B, C, and so forth, and these characters could be allocated dynamically because they came directly from the user input. So this object could be given a pointer to this other object that contains this dynamic information, or this pointer could be removed from the object. So that would be an example of pretty dynamic changes in the object state. Object behavior is generally represented by the set of operations that the object maintains and offers to its environment. So generally speaking, actions are operations or function calls or member function calls inside the object, and reactions are the values returned from the object. So the examples of these actions and reactions we've seen in our prior presentation, where, if you recall, we tried to demonstrate the creation of a heater class and a thermostat class. So these are the times where these two classes are created, and then the main function wanted to set the heating temperature on the thermostat, and the thermostat had access to the heater at runtime, and so it made a call to turn on the heater because it decided that with the setting of the heating temperature that was specified, the heater has to be turned on. So these are the examples of actions and reactions, and of course internally the reaction of the heater is to do a lot of different things to control the actual hardware, where it needs to do all sorts of validations and verifications of current conditions, where the heater can actually be turned on successfully or not, and so forth and so forth. So the behavior is revealed in its state changes. Okay, so once we attempt to execute different operations on our objects, obviously this will result in state changes. It's just like a user typing in a Word document. Every time they change a character, something changes in computer memory that is reserved to allocate that word processor text. So here we say objects can perform operations on behalf of other objects, and that again is demonstrated by this diagram where we had trying to demonstrate interaction between these two objects, heater and thermostat, that represent physical hardware. So objects may require operation from other objects by sending them messages. So message is a very generic representation of a function call or member function call of an object. So clearly, in order for the thermostat to be able to talk to the heater, what needs to happen is the thermostat has to have access to the heater name, or have a reference to it, or have a pointer to it, number one. And number two, it has to be aware that the heater does have available this operation named turn on, so that it can communicate it as a message by saying, I want you to change your state. Clearly, the state of the heater changes, whether it's successful or not successful change in its state, but that is definitely the outcome of this interaction right here in this example. Object identities are very important for object identification at runtime, as well as sometimes persistent layers such as database may generate unique identifiers for every record in the database, for consistency of records, for additional integrity checks of the data structures saved in the database. But at runtime, it's very often that we take the object address as its identity, and it's quite reliable source of identity. In addition, we mentioned here a message digest example where, for instance, the content of the file can be uniquely identified. So basically the idea is that if you take a specific file with some information in it and make a copy of it, it should be considered to be the same file, even though you could have placed it in a different location on your file system or giving it a different name. So here are some examples of from Wikipedia article on Message Digest 5 encryption algorithm, and it has examples such as, for instance, when you apply this specific algorithm to a text, the quick brown fox jumps over the lazy dog, you get this unique message digest, which is a 16-byte long or 128-bit long unique identifier of this message. So if you have a file with this content, then you can copy it multiple times, but this value will not change, even though external attributes of the file may change, such as its name or extension. Interestingly, a zero-length string can also have unique identity, and in case of MD5 hash, it will be this. So empty content still has a unique identifier under the rules of MD5 Message Digest 5 secure hash algorithm.